about to go we are about to go into a wonderful session. This is known as Big Science. So our conference sponsor, Brookhaven National Laboratory, as we know, is a part of the Department of Energy, and they're, as physicists, they're our family members, right? And they're doing amazing research in laboratories all across the country. And so in this particular session, what we're going to do is look at some of the big initiatives that are occurring out of the DOE and BNL in particular. Today we have with us Dr. Abhay Deshpande. Did I say your name correct, sir? Thumbs up. All right. My last name is Oluseyi. No one outside of this side of the Atlantic says it correctly, so I don't want to mess up someone else's name. So what I am going to do here is I am going to introduce our speaker now. So Professor Deshpande works in experimental nuclear and high energy physics. His current research, at least according to the Stony Brook webpage, includes various exploratory and precision studies in quantum chromodynamics using polarized proton-proton, proton-nucleus, and nucleus-nucleus beams of the relativistic heavy ion collider at Brookhaven National Laboratory on Long Island, and high-intensity polarized electron beams of the recently upgraded Continuous Electron Beam Facility, CBAF, at Thomas Jefferson National Laboratory in Newport News, Virginia. He has been deeply involved in the development of the science and promotion of the future Electron Ion Collider. And as I understand it, I believe you may have actually served as the director of that particular facility or something along those lines. And without further ado, sir, I will turn the floor over to you. Thank you.
Thank you, Hakeem. Thank you very much. Let me share my screen. And you should be able to see the screen now. And in a minute, you will see it in full screen mode. Do you see it? Yes. And you hear me clearly? Very good. Okay, thank you very much, Hakeem, for that introduction. I'm delighted to come and talk to you all about my favorite research project for the future, the Electron Ion Collider. It's a new collider we are planning to build at Brookhaven National Lab. And it is, I like to introduce its crux of its physics by saying that it is going to study a super God particle. Now, the God particle is well known amongst physicists. The Higgs boson was called God particle by a very famous physicist and became super important. It allows us to get mass, is what the claim is. And I'm going to tell you why I will call this particle, this physics, that we are going to explore to be a super God particle study. So with that brief introduction about the super God particle, let me dwell into the science and then the project, how we are going to do that. So the quest for fundamental structure of matter is universal. It is everyone who looks around in nature is curious as we grow up. And here is a little girl looking at grass and earth and probably wondering what's in there, what are we made up of, what is the smallest in this world, what are the fundamental particles that cannot be further divided. These are questions that we have all explored over years through school and our training. And over many years of study by humankind collectively over all parts of the world, we now know that the matter, this is a water droplet that I'm showing here. The smallest particle of the water is called the molecule. It's H2O. And then each of these is an atom. An atom has a nucleus in the center and electrons flying around it. The electrons, as far as we know, are not breakable. They're fundamental particles. But the nucleus has been broken about 100 years ago. And we now know that the nucleus is made up of protons and neutrons. The protons are positively charged and the neutrons are neutral. And then people have also explored around 1960 what's inside the proton and what's inside the neutron. And we now know that the protons and neutrons are made up of quarks, and they are built, they're bound together by something called gluons, the wiggly little things that are shown here. So this is something that we are going to study, how this proton comes about with these three quarks, and what is the role that this gluon plays. It will turn out that at the end of the talk, I will try to emphasize, and hopefully you will remember, it is the glue that binds us all. Everything that we see in the universe is starting from protons and neutrons. All elements in our Earth, in the universal, galaxies, everywhere you see, the fundamental thing that has everything embedded in it, is encoded in it, is this protons and neutrons. So we want to understand exactly how that happens, and how from these quarks and gluons all the visible universe is built. And based on some of the properties that I will describe to you about the gluons, you will appreciate why I said it is called the super God particle. So how do we know all these things? How do we know that the fundamental particle, how protons and inside there are the quarks and gluons? To understand that, I want to introduce first a concept of resolution. Resolution typically means what's the smallest size we can see. And here is a picture of a bad resolution picture. And maybe people can guess already with some background of United States and what's in the monument. It's one of the famous monuments. If I give you this hint, maybe you can judge, you can guess what that is. But I can also increase the resolution. What that means is that I have reduced the size of this hole, of this box here, to a smaller number, and you can start seeing a better and better figure. As you go to even better resolution, now probably people understand that this is a picture of the Statue of Liberty. So in going from the first part to what we have now, what we have done is we have increased the resolution. And that means that we have looked at finer and finer sizes. That's the history of how we went from seeing world as we see with your eyes, with using instruments to go into smaller and smaller sizes. Physicists know that that is called the resolution. The lambda is a resolution. Here is a constant. You don't need to worry about this right now. But what is important is that if you are measuring something with a probe, the momentum of that probe is inversely proportional to the resolution. So the larger the momentum of the observing probe, the smaller the resolution you get. And this is a simple message that you need to remember through this talk. So if we want to see small things, we need to use probes which are at higher momentum. And here's a picture of a microscope where we use the light in the lambda, the wavelength of about 380 to 740 nanometers. And the light reflects on it, and we see things that come out from here. And that has a resolution of about 200 nanometers. If you go to a better resolution device called the electron microscope, then you start seeing resolutions of the order of 0.2 nanometers, and the wavelengths of these, the electron beam at that energy of about 100 kilo electron volts is of the order of 0.002 nanometers. In high energy physics, we use the same thing. However, instead of using the electrons at 100 keV, now we have electrons at, let's say 20 GeV. Here is a thought experiment of a 20 GeV electron hitting a target, and then we put an experimental apparatus right in front of it and explore what comes out as a result of the collision. And that allows us to reconstruct the structure of that target, but with the resolution of about 0.01 femtometer, 10 to the minus 15 meters. So increase the momentum of the electron, and you suddenly start seeing higher, smaller and smaller distances. That means that we have very high resolution. And that's what has happened over the past 100 years for us to know that there are quarks and gluons, and there are electrons and protons and neutrons, and all the things that I mentioned to you before. So that's the concept. Now, what do we know now? Let's look at what our state of the art is. So here is the state of the art. Starting from a human size, we know that we are made up of molecules, and molecules are made up of atoms. The atoms I already mentioned to you is nucleus and the electrons, and we go down. And here is a big picture of a small proton. And there is 3 quarks there. There is bound together by glue. The distances we have gone from the atomic scale to the protonic scale is of the order of nanometers here to a femtometers here. So we are really now looking at extremely small distances. Now, I want to emphasize one thing. The interactions outside of the proton that happen here, nuclei and the atoms, are electromagnetic in nature. That means light, electromagnetic wave is involved. And those, the quanta of electromagnetic wave, are called photons. Inside the proton, however, is something called gluon that comes into picture that binds it together. And the gluon is a very, very unique and different kind of interaction. The photons carry no charge. So in field theories that we now know, the interactions happen only when there are charged particles. And photons are chargeless, as you know. Protons and electrons are charged, but photons are chargeless. So photons cannot interact with each other. However, very uniquely, gluons inside the protons and the quarks actually carry color charge. And that means that they can interact with each other. That means gluon can be exchanged by 2 different types of quarks. However, amazingly, gluons can interact with each other because each of them carry something called the color charge. And that is sort of mimicked here. Because of that, gluons can interact with each other, and a unique sort of circumstance evolves inside the proton. And that's what I will try to tell you here. So here is the center, and the right of your slide is the gluon. This is the wiggle that you see here, can interact with another gluon, and you can have an interaction that will be a 3-point interaction, we call it, because there are 3 gluons involved, and such an interaction can happen. You can also have 4 gluons interactions and 5 gluon interaction if it is possible. You can also have a simple interaction like this. The gluon splits into quark-antiquark pair. Both of them are colored, but all these 3 are possible inside the proton. However, when we look at the electromagnetic interaction, that means outside the proton, the only thing that can happen is this photon. Now, this is not the gluon, it is the photon, the light, that can split into quark-antiquark pairs, or it can split into electron-positron pairs. But there is nothing that allows us to do a diagram like that. A 3 photon interaction that looks like this cannot exist because of the law of nature. Similarly for this. And this difference creates all the richness of quantum chromodynamics or quantum color dynamics compared to the quantum electrodynamics. And this comes to haunt us in our experimental studies, makes it interesting but also difficult to decipher results. And that's why some of the things that we don't know about protons is because of that complication that is there. However, it's very fundamental to understand it. So what is our current state of knowledge? The standard model of physics, as you know, fundamental building blocks of nature, have these 6 quarks. Each of them have these 3 colors that I mentioned. They're bound by gluons. Gluons also have 3 colors. And then there are these light particles, the neutrinos and the electron, muon, and tau. They're called the leptons. And they don't have color, but they have weak charge. They have a different type of charge. Some of them are electrically charged. These things are electrically charged with a -1. And here are the charged neutral particles. Each one of them has an antiparticle. So there is a slew of particles, about 113 of them, embedded in this 4x4 matrix. Then there is this photon, the W boson, the Z boson, and last but not the least, the H boson, the Higgs boson. That was the God particle that was discovered the last amongst these in 2013. And then there is Einstein's gravity that sort of sits alone separately because it's not been quantized very well yet. It's not been unified with the rest of the theory. Amongst all of these, there are about 18 Nobel Prizes since 1950 already. And I think we are really exploring certain things about it that we still don't understand. Now, let me tell you about that mischievous gluon, or the super God particle that I mentioned to you. So here's what the reason for the Nobel Prize for these gentlemen, Higgs and Engler, were. They figured out that the mass of the quark was associated with this Higgs boson. This is a very fundamental thing. Quarks are very fundamental, and they need to have some mass there. Their mass in a proton with three quarks, it's extremely small masses. It's of the order of 10 to the minus 26 gluons with the 2 10 to the minus 26 grams. However, we know that when three protons come together and bound by the gluons, because they have to be bound inside the proton, it looks like that, but suddenly, magically, the mass of the proton increases by a factor of 100. Look at that, 1.78 goes to almost 168. That's about 100 times more. All of that comes from these gluons, which by themselves are completely massless, zero mass. So suddenly, you're realizing that you're getting into a puzzle that how can 1 plus 1 plus 1, which was this case here, was 2 times 10 to the minus 26, suddenly go by a factor 100 up. It turns out that it is because of the energy that is needed to bind these things together in this small volume of proton is such large that the gluons have to provide that energy. And that energy then can be looked upon from the Einstein's equation, E is equal to mc squared. And that mass that comes with the energy of that gluon is the one that is responsible for the massive proton that we see compared to the bare quarks. But amazingly enough, now what we have discovered by understanding this is that the gluons, which are by themselves massless, create the entire, about 99% of the proton's mass. Same thing happens in the neutron, and hence with all the nuclei and all the elements that you see around us in the entire solar system and entire universe, which means that the mass of the universe is coming from essentially 99% of the mass of the universe is coming from these massless gluons. And this is why I call it the super God particle. And I think something to be understood completely and very, very importantly. This because of the complications that gluons are inside the protons and they interact with each other, there's another very curious thing that happens. The atom, as we know it, and the proton, as we know it, both were discovered about 100 years ago, around 1920s and 1930s. That's when the atom and the proton were discovered. Today, we understand electromagnetic interaction, the photon interaction, which has no color, so precisely that you actually define time using those electronic transitions. And the current accuracy seems to be about 1 second in 220 million years. Think about that. That's the accuracy of the best watches, the clocks that people have built using atomic physics. Now, you ask the same question about the same 100 years later, how well do we know the proton, and were we to build a clock based on this interaction, how accurate would that be? And that turns out to be only 20 to 30%, which means that the accuracy in this time scale is about 20 minutes an hour. You would not use that clock at all. You could do better just by your human biological sense of what an hour is. So this is the complication that comes because of the fact that we don't understand these gluon-quark interactions inside the proton. And that's what we need to understand. The method we are going to pursue is something called a deep inelastic scattering. It is the best technique in understanding the structure of the proton and neutrons and the nuclei. And that's how we know most of the physics that we know today. And I'm going to explain to you what deep inelastic scattering means. So there is a famous quote from Richard Feynman that says, scattering of protons on protons is like colliding Swiss watches to find out how they are built. And this is what we are trying to do here, understand the proton structure. And that's what Feynman was commenting on. I would say that you can ask what is there. You can break the clock and see inside, all the, but you won't understand how it works. You won't find out from that scattering experiment or collision experiment how they were actually built or how they work. That would be a difficult question to ask. So what do you want to do? What do you have to do that? And for that, I have this pictorial explanation. Suppose I ask you, tell me what the internal structure of the watermelon is. And you do an experiment. You take 2 watermelons and you crash them against each other with high speed. And this is what happens. They break, and as a mess comes out, and there is meat, and the seeds are on the floor, and the green part. But you can look at this and say, aha, I have created a violent collision of melons, and now I know what's inside them, what is in there. And that's what we do at RHIC, the Relativistic Heavy Ion Collider, or LHC at CERN. What they do is proton-proton collisions or nucleus-nucleus collisions, and try to create if you want to study internal structure, that's what we would do. However, if I ask you, I don't want to just know what's in there, but how they were distributed. How were the seeds of the watermelon distributed? How were the meat was distributed? That's the question that can only be answered if I instead have a knife. A knife is something when I collide with the watermelon, it does not break. And you want an unbreakable tool to probe the insides of the watermelon, and so you can cut it the way you want, exactly the way you want. And this is what we would want to do with Electron Ion Collider. The electron is an unbreakable particle. We know that. And the nucleus is a complex particle which has the protons and neutrons, and inside them are gluons. So if you want to study the nucleus, why not study it with a knife which is sharp enough? And that's the electron that we will try to use. And here is the Feynman diagram of a collision. This is just a diagram, just a schematic thing. Don't worry about the technicalities. The electron is coming here. It is exchanging a high energy virtual photon. The photon has a wavelength which is smaller than the size of the proton, so it can go inside. And that's the reason why I call it deep inelastic. It goes deep inside the proton to look inside. And it can only go there because if the wavelength of the lambda, that wavelength is smaller than the size of the proton. And that's the proton. And then whatever remnant I can see, and I can also see the electron come out as unbroken, because it is unbreakable in the first place. So the knife remains the same, but I can cut the watermelon exactly as I want, and I can study it very carefully. That's the method we are going to use. So now with that introduction, let me come to the more practical things of the electron ion collider. So what do we plan to do? We want to have electron nucleus collisions. That's like bottom right here, electron coming from this side, proton or nucleus coming, and the electron scatters off, and then we'll study what happens. And for that, we need two rings, two counter-rotating rings. So this is the blue ring of the nucleus, and this is the red ring of the electron. And at some point in the interaction, this is called the interaction point, where they come together and have a big scatter, and that's what it looks like. So that's what we want to do. So let me give you a flavor of the physics of the EIC, the Electron Ion Collider, in very short time. So here is the evolution of the universe. It started with a Big Bang and sort of exploded at some point, and today is shown here with the human being shown here. So on the way there were particles formed. The particles came together to form light nuclei. They came together to start building bigger and bigger nuclei. This is the formation of all the nuclei. Nuclei came together to form various galaxies and structures. And then today is a cold structure, and we can see all the universe. So this is the time evolution of the universe. If you want to study what happened in the big here, what we need to do is to use colliders, and that's what they do. The RHIC, the Relativistic Heavy Ion Collider, with nuclear collisions, they collide each other, and they go back in time in the energy regime that is shown there. The LHC goes a little bit further and goes all the way up to that point. Now, if you want to study how these things were formed, the Electron Ion Collider will span the area from that, where just the protons were being formed, all the way to where the nucleus was being formed. So all of this has to be studied very carefully and precisely. And the precision comes from the fact that we are now going to use the electron as the probe, and the breadth of the nuclear size that we want to use in the collisions, from protons all the way to uranium, allows us to understand how the nuclei were formed in the early universe as we went up in time. So all these questions were summarized into three simple, easy to promote questions. One was, how are the quarks and gluons and their spins? The quarks and gluons have a property called a spin. They have orientation like small magnets. And that is shown here. The protons have that, and inside them, there are the quarks which also have them. But it turns out that how are they distributed in the space and momentum? What are they doing in terms of momentum? Are they moving? Are they not moving? All those questions remain. And this is the first question we want to ask. How do the properties of the proton emerge from the interactions of the quarks and gluons that they are made up of? That's the big question that we want to understand. With nuclei, I would like to go inside the nuclei and study what happens to an interaction for a color particle inside a proton inside the nucleus. If I push it very hard, how are these interactions happening? And at some point when the quark wants to come back, it picks up. We observed that it is only picking up a particular kind of its antiparticle, and it forms a color neutral object. We have never seen a quark isolated in the laboratories. We have only seen quark and antiquark together. So why does that happen? Why is there a color neutralization or fragmentation into something like that? We don't know, and we'd like to understand that better. It's a very critical and important aspect of QCD, and the color is playing an important role there. And the last but not the least, what we have noticed is that at extremely high energy, the number of gluons in the protons increase. We did that experiment some 20, 30 years ago in Europe and other places, and we found that as the energy goes up, the number of gluons goes up. So the question is, what happens in the nucleus? We have lots of protons and lots of neutrons. Can we look at nuclei at extremely high energy and find something unusual? In fact, there is a good reason to look there, because some of our own theorists at Brookhaven Lab have actually predicted a very different kind of medium that is being created as a result of very high gluon density inside the nucleus. And if it exists, it has very, very interesting properties. And we would like to, not just we, but the entire world now appreciates the importance of that prediction and that study. And we all want to go and study if that is true. And that is called color glass condensate. And it is a result, I will talk about it a little later, but it's some sort of complex object that is formed by a very high gluon density. So does it really exist? And something that we would like to explore. While I don't have to say that explicitly, again, if I don't understand the structure of the proton, I don't understand what it looks like in the transverse dimension. It's obvious, right? We have zero knowledge. If a proton is coming at you, if you're looking at a proton coming at you, the transverse distances, if you're able to see the transverse distances and explore them, we can study them indirectly. That understanding is really not there. That these are different types of models that people have built over the last, 50, 70 years, the bag model, the constituent quark model, the lattice gauge theory that tries to explain. They have different properties. In this one, the quarks are the three quarks, and the gluon sort of sits around it. In this one, the gluon sits around each of the quarks and closely hugs it. And in this case, the gluon sort of sits inside between the pointing of the three quarks. What is real? Is it true that we can go from different energies from here to there and really study this as a function of energy? Is it really true that this is what happens? We just really don't know. And so understanding of the proton structure, one of the things that we have ignored so far is this transverse imaging of quarks and gluons inside the proton. So this is a must program for the future collider that we're building. So how are we going to do that? So here is what we are planning to do. Now you can see that this is a one-dimensional object of a human being. Yeah, seeing this, you know that this is a human being. But really, we know that this is just one-dimensional projection or a cartoon of a human being. The real person looks more like this. And that is the relevance of the proton that I showed you, barely showing only three quarks, now filled with gluons and having a rich structure and three-dimensional object, which means that they have to be in motion. And that means that motion means that they might have left-right motion. They might have circular motion. That means the quarks and gluons might have orbital angular momentum. And we need to understand, but also measure effects of those experimentally. And that's what we are trying to do with the Electron Ion Collider, never done before in any previous experiment so far. So again, coming back to showing you, you had an idea. Probably some of you or many of you might have actually figured it out before you reached this level of accuracy. You might have found it here. The reason you had an idea is because the roadmap that you had, you have seen the Statue of Liberty. You have some idea what looks like one arm going up like that, and this pointy things on the head. So you get a picture even before you know, so you can extrapolate your mind in the vision of your mind. However, if you don't have any idea, as we don't have any idea about the transfer structure of the proton inside, then it is very difficult to judge. So you really have to have lots and lots of data to measure that. And here is the illustration based on a similar picture. This is the resolution, a bad resolution picture of something else. And you realize that I have to show you many more steps before you can figure out what this picture is about. And you can try to see in your mind if you can figure out what it is. At this point in the previous picture in the Statue of Liberty, you already knew what this was about. But most of you probably don't know. Those of you who are artists in the field might have figured out what it is, and I have experienced some students already know this, is that this is the persistence of memory painting by Salvador Dali. And the point I wanted to make was this is all unusual, and we don't know what the landscape is, similar to the one that we don't know inside the proton, and it takes a lot more data, a lot more precision, a lot more higher resolution to understand what's going on in this picture. So how do we do this? So the first and foremost, we need to figure out how to measure these transverse momentum and position distributions inside the proton of a quark, for example. Here's a quark who is sitting at a distance bt from the center of the quark, assumed center of the quark, and it has some motion, so it has some momentum as well. And you can perform an experiment. If it has a motion, remember, it cannot leave the proton. That means it has to turn around at all times as soon as it comes to near the boundary of the proton, and that's what is happening here. And the quark is rotating like that. And if I hit it with a photon, it starts moving, but it has a motion in that direction already. And now I create a motion in that direction. The resultant motion is here. And as soon as it starts leaving the proton, it picks up an anti-quark. This was the quark, anti-quark, and forms a particle called pi plus. So a particle is picking up an anti-quark and coming out this way. If the quark was moving in the opposite direction, it would have come on that side. So we have in experiments measured left-right asymmetries for pi pluses, pi minuses, kaon, different particles that come out like this. And from that, we know decisively that there is a left-right motion of these quarks. There must be an angular momentum. And we have built pictures based on simulations of these preliminary studies that there is a kx, the momentum in the x direction, momentum in the y direction of a proton, which is polarized in that direction. There would be a clear imbalance around the zero of kx. We don't know whether it is true, whether this is the distribution, but the current knowledge, which is rudimentary, allows us to extrapolate that. We want to measure that in the future experiment with high luminosity or a high number of events in a collider. Now, that will give me a momentum. But remember, angular momentum requires you to also know the position. Remember, in your undergraduate physics, you learned R cross P was the angular momentum. And I just told you how to measure the P. But what's the R? So here is a method that we have just discovered. When I say just discovered, in about last 15 years or so, how to measure the position of it. And that is done with a non-violent collision. Non-violent collision. What does that mean, non-violent? Remember, every time I mentioned to you before, I have gone inside the proton and I have actually broken the proton. And that's how I look inside. However, if you want to study the structure, the distribution of the proton and its motion, this is not an option for you. You really cannot destroy the proton. It means that you need to figure out how to do a non-violent collision. And growing up in India and now in the US, you can figure out that when I can think about non-violent collisions, I think about these two people who were the origin of the non-violent movement. And I want to measure that in physics. What is the method that we use? So the method that we use is this following. Here is the proton coming through. Here is the structure of the proton. I shine light on it. This is the light from the electron. The electron ion collider is sitting here. And it shines light. It interacts with the quark just so lightly. It went inside the proton, but interact with the quark just so lightly, not violently to break the proton. But at some point, it also de-excites the quark inside, excited and de-excited, through this evolution, this emission of the photon, and the proton remains intact. In the Electron Ion Collider, we want to measure such a thing. We also want to measure the thing in which the interaction is initiated by a gluon, and then there are some quarks involved, and what comes out is not a photon, but something called a vector meson, which is a combination of quark and antiquark. That tells you something about the gluons. So once you have these two kinds of measurements, you can access where and what momentum and what position these quarks and gluons were inside. And this is why it's very important. What we call that is, technical term is generalized photon distribution function, but it's only telling us the spatial imaging of quarks and gluons. So that's what we want to do. And we want to measure that very precisely in the future collider. Why do we want it? So we want to make the transverse momentum distribution like this on the left-hand side, and position distributions of these gluons and quarks inside the proton. And again, these are models that are built from very rudimentary ideas and data that we have so far. We don't know, it may not come out to be this way. We might discover something completely different. So summarizing that case, in the case of the watermelon, we saw that was the nucleus collision at RIC. This was the one that I first told you about, to look inside. But here is what I really want to do in the future. That is the MRI, the magnetic resonance imaging, without breaking the watermelon. I want to see inside the watermelon and understand the location of various things, but also the motion of various things. As soon as I break that watermelon, I will lose all of that. I will probably gain the position, as I've done in the center here, but the motion is definitely gone. And I want to keep that, want to understand it. And that's why this is a very unique and different way of doing it. Last but not the least, I told you that the gluons interact with each other. It's called self-interactions. And if you can imagine the gluons splitting into two, as is shown here, then the two can split into further two, and that can go into further two and further two. And in fact, in his Nobel lecture, Origin of Mass, Frank Wilczek talked about this. He said a self-catalyzing enhancement that leads to a runaway growth that is shown here. So a small color charge in isolation can build a big thundercloud of color. This is what is written, and it's true. It should happen. However, does this happen forever? Does it mean that there is a gluon density that keeps on rising inside the proton as you go to higher and higher energy and smaller distances? No, that would be an infinity, and physicists don't like infinity because nature is not infinite. It has finite. You know that the size of the proton is finite. The mass of the proton is finite. The energy inside the proton is finite. So it cannot be infinite, but somehow the theory is telling us that something new has to happen to make this infinity go away. In fact, our physics friend at Brookhaven lab figured that out. They said, oh, well, there is another interesting thing that happened. Here is what the explosion might look like, but now we are inside the proton, which means that there is a finite volume, and these gluons that are splitting into 2, 4, 8, 16, they will start getting very crowded, which means that there will also be an opposite process where instead of splitting, there is a merging of gluons. So these two will merge to form one, then that and that will merge to form the other one. And so finally, the gluon number keeps on increasing, but also starts decreasing. And at some point, there is a balance that is formed between the splitting and the merging. And that balanced state has the unique property, which has been called the color glass condensate. It has a density of 50 or 100 times of the neutron star. It has it looks like a brick wall. It's like a very, very hard wall. You can't cross it. Very interesting properties have been predicted. And of course, it is a fundamental thing in the nuclei. Every nucleus that will come up at high energy should have that inside it if you explore it appropriately. It's a very curious thing, and we want to measure that. It's a saturated state of gluons is reached, and that's what we want to measure. I want to skip this quickly. This is the history of proton structure. This was a proton intern structure, the internal quark structure, and we want to measure these two things to go to a gluon saturated state in not just protons, but also in nuclei. Freeman Dyson was a great physicist, as you know. He always said that the new direction in science are launched by new tools much more often than new concepts. And there I see that we are now launching upon is a new tool. And this is the conceptual design report. This is the science document that was created. It is being built at Brookhaven with a partnership with Jefferson Lab. Sorry, this needs to be fixed. Jefferson Lab at Newport News. And what we want to do is to install the electron facility in the same tunnel that we have the RIC, and then inject the electrons from one side and then collide them in up to 2 different experimental positions, one here and one there, and to do the physics that we want to do eventually. When built, it will be the first electron-proton polarized collider, and the first electron-nucleus collider. And this is how the complex will look. As I mentioned to you, the current existing RIC is shown here, and that will be replaced with the electron beam inside, and that would be the locations of the 2 proposed detectors. And this is how it will evolve. RIC will run until 2025, and beyond that, the Electron Ion Collider will become the main workhorse of QCD around the world. It is going to be a very unique machine. Why is it unique? I've plotted the center of mass energy, the total energy of the 2 collisions that you can create and use to study. And on the y-axis is the luminosity. The luminosity is the number of particles that collide every time the bunch goes across each other. The electron bunch goes across the proton or the nucleus. So you can see there is a huge range of experiments. You can see that you can go to 10 to the 38, but the center of mass, the energy is very small. As you go to higher and higher center of mass energy, this luminosity number falls very rapidly. So the past experiments are here, and the EIC is trying to push the boundaries by going to a high luminosity, but also high energy. So in that direction, this will be the variability here. And these are very, very far future experiments that are being planned outside in the world. But if you ask, what is the, is there a width in the flexibility of the collider, then most of the other fixed target experiments go away. And if you ask which of those colliders that are being thought about, even in 50, 70 years in the future, which of them can do polarization? That means that you can study the proton structure with these quarks and gluons flying around with the spin in mind. Nothing remains. So that's a unique machine, not only from the past, but also for another 50 years in the future. That's why this is a very, very unique place to do science, and will be. Those who are slightly older like me, we grew up with Star Trek, and maybe there are more later versions of this, they would say this was meant to go boldly where no one has gone before. And I'm coming to tell you that this also, the new collider that we're building, is, and from the physics side, this is a variable that we use for X, the momentum fraction of the quarks, versus the resolution that I was talking about. And all the past experiments are sitting here. And this is the region of this space, which is completely unique, and no man or woman has actually explored this very well. And similarly with nuclei. So it is going to be a very unique machine, not only because of its inherent properties like the spin and the luminosity, but also where in the region of the nucleus, how deep can it go, how small values of the momentum fractions it can see. It is going to be a unique machine. Now, how do you plan to measure these things? So here is a cartoon of a detector. Here is a detector. There is a particle coming, the ion is coming from this direction. The electron beam is coming on this direction. Of course, I have exaggerated this crossing angle. Normally at the collision point, they are back to back, or very small angles, like a few milliradians. You can't have 13 or 10, 20 degree angle as is shown. This is just a cartoon. But when the collision happens, particles start going, and this is the central detector, we call it, and that has traditionally been the norm in all past collisions. They've always built the central detector to measure everything. However, they always have missed what happens to the electron beam afterwards, or whatever comes out in this direction. And most importantly, they've always missed the part of the fragments of the nucleus that go on in the very forward direction. So that is the unique part, unique thing that we are trying to do. We do not want to leave any part apart. So we want to measure everything that happens in the collision, not only in the central region, but also in the forward acceptance and the backward acceptance. So a total acceptance detector has to be designed for a future experiment. That has excited a lot of people. We have a user group, which is now spread all over the world. And this is the map of all the institutions that are there. There are more than 34, 35 countries, 230 institutions around the world, and around 1,300 PhD physicists, not counting the students yet. They have probably equal number of students who are going to be aspiring to do science here. And those are going to be coming in. There are 46% of the users, the potential users, are American, 30% Europeans, 20% Asian, and smaller parts from Africa and South America. I think this is going to be a wonderful international place to work, to mingle with other cultures and do science together and bring the whole world together for the science. So there are 4 detector ideas now being pursued right now. One is built upon, I told you this complete detector is needed. One is built upon an existing detector at Brookhaven Labs, which is called the S-Phoenix detector, a super Phoenix detector that is built to study the nucleus-nucleus collision. It is a central part of that future detector. So what you see in blue here and the yellow and the inner red part is the S-Phoenix detector about. To that, people say, well, let's use that in the future and build something in the very forward direction in which the proton or the nucleus will fly, and in the backward direction, the electron will fly. So some of us are working hard to build this end of that detector and that end of that detector, to upgrade the existing one, to minimize the cost of the total project, and to use maximally the investments from the Department of Energy. And this is an idea that is being produced, and some people are pursuing that. Some of us are doing something different. They say, well, we now have a different machine. Let's build what would be the ideal detector for such a machine. And they came up with a totally hermetic electron nucleus apparatus called Athena. And this is what that looks like. Now, in proximity, it doesn't look like functionally very different. However, in details on the back and the front, they are different. The functionality is the same, but the ideas that have been pursued are slightly different. And this is the 3-dimensional rendering of the proto collaboration that being formed now. There is a third one that says compact detector. They want to build a very small detector. These are like the sizes of 747 jets, okay? Engines, not the jets themselves, the engines of the jet. So a human being standing here would be of that size right there, and a human being standing there, or maybe standing here already. So it's about this size, the size of a human being. This one will be about a third of that. It's really small. I can probably put my arms around the entire outer rim of the detector, so about 1.5 meters or 2 meters. So that's something that they want to build. And the reason is they're proposing a smaller one is something that they say, okay, if the smaller, the better, it will be cheaper. If we can use modern technology to enhance the functionality in a small size, then let's see if we can build a cheaper one. And that's the rendering of that one. And then there is another group that is trying to see what other physics can be done with a detector that will be dedicated to a smaller center of a smaller energy. You see, this machine is able to run not only at the top energy, but everywhere in a very wide range in it. And this group is trying to figure out if there is a case to be built to build a detector that will focus only on the lower energy in a collider mode. So we'll see what happens. I think these are the web pages of these 4 initiatives that have come up. And eventually we will build 2 of them. Hopefully we'll be able to build 2, one immediately when the machine comes on, and one a few years later. So that's what we are planning to do, to build about 2 out of those 4. And a process of decision making is about to start, et cetera, et cetera. So coming to my last couple of slides, this is the reference schedule. This is where we are right now, between 21 and 22. In the parlor, the technical parlor, we just got something called the critical decision 1, which allows us to go forward to create a realistic engineering design for for an approval in CD2 in about April of 2023, and a CD3 in about another year from them. And the construction of the machine itself starts at what is called critical decision 3. So this is where the construction will start. It will go until about 2030 or so. There could be first collisions in this part, the blue, dark blue regime here, which is called the CD4A, which is not a physics time to start, but just the engineering time to start. Meaning, when accelerator folks build this new collider, they need to get some time to understand what the machine looks like in terms of operation and fix all the anything that might need fixing. And for that, we need a rudimentary detector ready to take data at this point. So at the first detector that we want to build should be ready to take data at that point, not in its full glory, but at least allowing enough feedback to the machine physicist to improve the machine. And somewhere around 2032 or 33, that's when we want to have that detector ready to go and complete and get to take physics. That's around a range around which physics will start at this future electron ion collider. So let me summarize. I hope I have told you that it's the color inside the proton, the neutron is the mischievous colored gluon, or the super God particle that binds us all, is the crux of the electron ion collider science. The US project has significant momentum. It has been approved and blessed by the National Academy, and the Department of Energy has taken that over and run with the users and the two labs with them, moving towards realizing the next frontier in QCD called the Electron Ion Collider. It's a very, very exciting time ahead for those people, especially who are now college students, physicists, undergraduate, as well as graduate students and postdocs. This is going to be the machine on which you are going to work. I will be very old by that time. I will be enjoying the results that you produce with that time. So we are looking forward to getting a lot of young people in and get involved into this study. So it's a really exciting time. Get involved. Brookhaven is there to welcome you all to do this experiment. If you want to read more about the science of these are 3 articles that were written over the last 3 years. So I'll stop at that point and happy to take any questions and discussions. Thank you.
Thank you, sir. That was a very excellent presentation. I'm always inspired when I hear particle physicists, high energy physicists discuss the proton. In fact, one year on my Twitter, I said we should have an International Proton Day or International Day of the Proton.
I will vote for that.
You're down for that. All right. So here is a question from myself. I am not a high energy physicist. And there are things that I have, now there are other questions in the chat, but I'm using my power to ask my question first. Now, it used to bother me that, okay, all electrons are identical, all protons are identical. The electron and the proton have exactly equal and opposite charge. What great coincidences, right? And then I talk to my particle physicist friends. They're like, well, the reason why all electrons are identical because there's this thing called a field, this field, and there's just excitations in this field. But as we describe the proton, there's so many, there's so much internal structure, degrees of freedom. Are there potential measurements that could be made that captures what those differences may be due to those internal dynamics?
So the internal dynamics is such that it's amazing that although the quarks and gluons, their interactions are very complicated, their alignment and their interaction, their alignment and their orbital angular momentum gives the proton its spin. Let's take the spin example, a spin of half. You've never seen a proton with any spin other than half, right? It is one unique thing that is so strongly adhered to. It can be in the lab in atomic physics, or you can put it in the LHC and accelerate it to TeV. The spin does not change. Relativistically, the mass changes, but spin doesn't change. However, then you ask, does the internal dynamic change when you take the proton from the atomic physics lab to LHC? And there the answer clearly seems to be yes. Which means what? Which only means that the probe that when you scope, you scale the inside of the proton to see the proton. That is what is impacting what is seen inside. However, somehow the proton manages to keep that spin half. The contribution from gluons to quarks to orbital angular momentum can change among themselves as you go to different scales, but never will it violate that sum rule called the spin summing to the spin half of the proton. It's always half. Yeah.
And this energy of that, how the gluon density increases at higher energies. We're talking kinetic energy. So you can switch frames and have a potentially different kinetic energy. So
yeah, but these are relativistic, right? So you're relativistic. Now you're now changing things at a very minute level. Once you reach relativistic energies, then you're in trouble to get into a very significantly different argument. Yeah, you cannot use the Newtonian arguments anymore. You're always in. You have to keep track with Einstein.
That's right. All right, so I'm going to go to questions that are in the chat. The first one comes from Amber C. Rodriguez Alicia. Forgive me if I mispronounce. I've done my best. So the question is, why don't you see formation of heavier atoms? And what I'm guessing is what they're referring to is in proton-proton collisions. Why don't you see something like deuterium form? I'll continue. Is it in theory possible that in the collision, two protons turn into neutrons and a helium atom is formed? And you have all the ingredients after all, even the binding energy.
Yeah, so all of that can happen at low energy. Under good conditions, under specific conditions, you can actually bring those things together. But the energy that we're talking about in a collider, we are not. I mean, these two protons are instantaneously forming. Basically they're blowing each other out. Then there is energy so high that binding that is needed immediately after they're breaking to keep the quarks together, instead of 3 quarks now to form a 6 quark system, that energy is too great. So these quarks just fly away, picking up anti-quarks and the C gluons, et cetera, et cetera. So it's a question of how fast things are happening. Yeah. So if you have a large energy, then you can't have these mergings. What can happen, and that happens in high energy nuclear collisions, as we do at RIC right now. Let's take a not just a proton, but let's take a nucleus and nucleus. And then we have collided them, and we see something called quark-gluon plasma, where these quarks and gluons seem to be, at least instantaneously in time, have sort of melted for a while. But it is at high temperature, melted, okay, at high temperature, but it starts cooling very fast. And as soon as it starts cooling fast, it starts creating particles. And those particles can be helium. They can be bigger particles, helium. I mean, we have seen helium come out in another one of the experiments. So that can happen. The process is different, though. As far as I know, I haven't seen proton-proton collisions in experiments to see helium. But it is the indirect process of actually forming a quark-gluon plasma, then cooling it down, and during the cool-down process, other particles are formed. That we have seen. Yeah.
Okay, so the same person has another question, which is, what if instead of decreasing after too many gluons have been created, they just separate into a new proton? This would mimic how new pairs are formed when you try to divide quarks.
It could happen. It could happen. I mean, but for that means that you need to break the nucleus itself. Yeah. Yeah, break the nucleus itself. So there is one thing that I mentioned to you. Remember, at this highest energy, these protons and nuclei, at the place where these high gluon densities are being formed, that is so high in gluon density that it is like a brick wall. You know, think about it like a diffractive experiment, a diffraction, undergraduate diffraction. It's a disk, and you shine light on it, and you see diffraction pattern. But the cardboard on which you're shining the light doesn't break, right? Because it's hard, it's opaque. It doesn't allow that. So in our experiment, the nucleus becomes that hard object of only gluons. There are no quarks at that high energy, okay? So it's a gluonic wall that is being created. And that wall is so hard that you shine something, it will just diffract, like the pattern of particles, like the real diffraction pattern. And that's one of the signals that we will eventually hope to see in the Electron Ion Collider. Yeah.
Very good. So do we have other questions from the, I found another one. Amber again writes, What exactly is color? I know it is the charge of the strong force, but I still don't understand what properties of a particle change when they change color. Does the particle type change?
Yeah, so it's a good question. It's when people discovered electricity, they discovered that there was a type of charge on my hand on the right hand side and another type on the left hand side. And they knew that when they come together, they actually attract. And then there's so as a convention, they called it positive charge and negative charge. There was no reason to call them positive or negative. There will be +1 and -1. It was just it's a convention.
Right.
Now, when there were only electric case, there was only two charges, positive and negative. So we could figure out everything based on that. However, as we understood more about the structure of the proton, there were scientists in the 1960s who were thinking about it, realized that to explain all the particle zoo that was being discovered in the 60s and 70s, the basic fundamental particle or building block of that had to have not one, but three things, three charges, which were distinctly different than just the electric charge. So you had to come up with something that could be, they could have done +1, 0, and -1. If they didn't use the +1 and -1 for electric charge before that, this could have been a way to go. However, people 70 years were using positive and negative already. So they had to come up with a different thing because they were clear that this is a different type of charge, different type of property of a quark that had to be assigned. So they called it color. It was, I think, poetic. It was just why? Because the three fundamental colors in visible spectrum actually make the color white. Okay? Because I told you that you have to have a color neutralization in all the things that we see. We don't see color independently. We don't see a quark independent in nature. We always see a quark and an anti-quark, or a three quarks in the proton in such a way that the colors are neutralized. So it's a white object in that sense. Yeah. So all of these analogy that people knew from the painting of the color of as an artist went into this picture because it aligned with that analogy. It was nothing special, but it just fits the picture well. Yeah. More figuratively as well as literally. Yeah. And that's the reason why that
three primary colors, right?
It's a three fundamental colors that you need to build the entire universe that we need, right? What we see. If it had been 4, 5, I don't know, people would have had to come up with something else, but it just fit with 3. Yeah. So it's something that nature is how it is. Why exactly 3 color? Maybe you will discover eventually. You do experiments. Amber, is that right? Amber was asking that question.
Yeah. So I have a different question, and it has to do with the energy of the protons. But I guess the question is that if you have a high energy proton colliding with a very low energy proton, is that something that's been done? And when you,
yeah, people have done that. So the people have done a proton accelerator hitting a fixed target of zero energy, fixed target.
Right.
That has been done in the past. Yeah, that has been done in the past. But what happens is when you have both proton and the target, and the probe and the target moving, you get a very big enhancement in the useful energy that you can use to study the physics.
Right. So I understand.
What we call is the fixed target experiment versus the collider. The collider has some very distinct advantages because the two beams are moving, or particles in two beams are moving. There is a huge enhancement in the usefulness of the collisions. And so if you are spending money on electricity and all the people and running the lab, you better make the maximum out of it. So you could either go to a TeV. I mean, in fact, let me give you a very clean example. If you wanted to do what we plan to do at the EIC, we had the electron beam of about 10-20 GeV and 250 GeV proton beam. The effective energy that we get is of the order of 140 GeV. If I were to do that experiment with a fixed target experiment, that means keep the proton or the nucleus stationary and hit it with the electron beam, I would have had to create a tera electron volt electron beam. It doesn't exist Yeah.
Wow.
So now by doing a 20 GeV electron and 250 GeV electron proton, we are already reaching that limit that you could never reach for technological reasons. Yes.
Right.
So that's the reason why a collider is a very, very interesting, and nature gives us that. Why not use it, right?
Right, absolutely, absolutely. This has been a wonderful and excellent presentation. Thank you so much, sir.
Oh, you're most welcome.
Yeah, and you know, you were very thorough, because I was going to go into participation by membership, and you covered that as well. So you're located at Stony Brook, and most of your research takes place at Brookhaven National Lab. That's
Yes.
correct.
Yes.
Your experimental and
That's correct. Yes.
use there. Right. So thank you very much. And I'm going to turn over the floor to our student representative, whose name I have learned to pronounce correctly. It looks like Farah, but it is not.
Oh.
It is Farah.
Oh, really? Oh.
Yeah, like far away.
Oh, okay.
Yes. And here she is. So I tell you, sir, we have an amazing crop of young scientists. I've been working with the young scientists this year. So, and she is one of them. So I'll turn it over to her. Thank you so much.
Great. Thank you.
Hello, everyone. Thank you so much. Thank you so much for joining this session. So I just want to point out that we still have some amazing sessions to come. So we will have some special events. We'll have a session with HBCUs. So department chairs, faculty, students, and friends of HBCUs, please be sure to engage in that informal chat session happening at 5:30. We'll have a survey and evaluation team as well in our session headed by Dr. Darnell Cole. We'll also have a special seminar by Dr. Tracy Slater, so be sure to check that out as well. Don't forget to stop by our exhibit halls, which will run for the rest of the conference. Tomorrow, we have an amazing lineup of events, and we will kick off with, of course, our poster walkthrough, which will actually be in Gathertown tomorrow morning. And of course, our exhibit halls will be open tomorrow morning as well. So be sure to check those out and to join early for those sessions. So I want to thank you all again, and I want to at this time recognize all our sponsors or co-partners, Brookhaven National Lab and Associate Universities Inc., AUI, or gold sponsors, Corning Inc., National Aeronautics and Space Administration, NASA Goddard, National Radio Astronomy Observatory, or silver sponsor, Optica, formerly known as OSA, or bronze sponsors, Facility for Rare Isotope Beams at Michigan State University, Morgan State University, and University of Notre Dame. As well as I'd like to thank all our 50+ exhibitors for supporting this conference. Thank you very much. And now I will turn back over to our president-elect for closing remarks.
Thank you, Farah. This is what is so wonderful about coming to the NSBP conference, is that we get the great science, we get the great scientists, we get the opportunities, we have the fellowship of our membership, including our students, our elders. And I have to point out that Dr. Sakazi Matingwa, your colleague, also gave a shout out to what an amazing presentation that was. So I encourage everyone to continue to participate in this evening's activities, and we'll be back again tomorrow morning. Big science. This is a new thing that we've done here this year at the National Society of Black Physicists Annual Conference. And what this is about what's coming down the pipe. These are the big science ideas that are going to make the very fundamental breakthroughs and insights into nature, that which brought us all into this, right? We all have the curiosity about the universe in which we live. And so this has been the very first presentation. It's incredibly insightful as well as interesting. And so those of you who are students, we have a very strong high energy community, and there are many directions that you can go. Protons I love, neutrinos I love, and we all love new physics. So hopefully, I just saw an announcement that LHC may have seen something again, but you know how that goes. All right, so it's what we do rigor. We do rigor in physics, so you know bumps can disappear. So thank you all very much for participating, and I will see you at the next session. Thank you.